Today, we're going to learn how to conduct a Z-test and a one-sample t-test by hand. Stay tuned. So far on this channel, we've talked about a lot of important concepts that are foundational to how a t-test works, especially standard deviations, sampling distributions, signal-to-noise ratios. If you haven't seen the videos on those, I highly recommend checking those out first and then coming back to this video. If you can't do that, it's okay, but you may not get the full experience. Today, it's time to put all of that knowledge together and actually conduct some statistical tests. The one-sample Z-test and the one-sample t-test. We're going to do the Z-test first, but if you're here for the t-test, trust me that you should watch the Z-test part of it because, spoiler alert, the calculations are the same. Shh. So we're going to start with one sample test, meaning that we're comparing a sample against a known mean. Imagine that we have a sample of participants and we want to know if they are different from the population. For example, my cousin owns a bagel shop. I read it in a recent journal that the average American adult eats 2 bagels per month. Now my cousin's trying to figure out who to market to in order to get more customers. Based on her current customers, she thinks that older people might be likely to eat more bagels than younger people. She's considering buying some radio ads on the oldies radio station. But before she spends any money on that, she wants to know for sure that oldies station listeners are different from the general population in terms of how many bagels they eat. So I've collected bagel eating data for a bunch of oldies station listeners this past month. The problem is, we know we might get a number above or below average just purely due to chance. What if we happen to pick oldies listeners who just naturally ate more bagels, but it has nothing to do with being an oldies listener? We just happen to get a high number in our sample. So how do we find out whether our difference is real or not? If you've seen my videos on signal-to-noise ratios and sampling distributions, you'll remember that we need to separate the signal, that's the difference from our sample and the population due to our manipulation, and the noise or error, the difference from our sample and the population that is simply due to random chance. So we really need 2 pieces of information, signal and noise. Now the signal is easy. We calculate the average of our sample and subtract the population mean to get a difference. So when we convert that to symbols, it becomes x bar minus mu. So x bar minus mu is going to go on top for the signal to noise ratio. The second thing we need is a measurement of the error. We don't really know how much error we have, but as we've discussed in detail in the sampling distribution video, we can estimate it using our sample standard deviation and the sample size. The formula for this estimate, which we call the standard error or standard error of the mean, looks like this. The sample standard deviation divided by the square root of the sample size. So this is our final formula for the signal to noise ratio, which is going to spit out a number or a calculated statistic like T or Z that will tell us how likely or unlikely our result is due to chance.
Come, it is time for the ritual. Let the calculations begin.
Because we have our known population mean, the data are normally distributed, and we have a lot of data, more than 30 data points is usually considered a lot, we can do something really basic called a Z-test. So here's my sample in list X. But to keep things simple, I'm going to pretend that I have a lot of data, and we're only going to calculate by hand using force so you can see the process without getting bogged down. Now, if you want to make a list that is 30 data points long, feel free, and you can do that as practice. But you can imagine how this would look with a bigger data set. So let's start by setting up our hypotheses that we are testing. Our null hypothesis is that the population from which our sample is drawn is the same as the general population. In other words, the mu of our sample is the same as the mu of the general population. The alternative hypothesis is that our sample is drawn from a different population than the general population. In other words, the mu of our population is different from, or not equal to, the general population. Note that these are mutually exclusive options, and only one of these options can be true. Now, we need to figure out what number we would consider not just due to random chance. In our case, we will set alpha to 0.05, meaning the outcome will be due to chance less than 5% of the time. Remember that one time when we did z-scores? Good times. Good times. Anyway, we're basically doing that using a z-distribution, or standardized normal distribution, to test against our population. In this distribution, 95% of the data falls between values of z that are equal to negative 1.96 and positive 1.96. Samples drawn from that distribution will only fall outside of that range 5% of the time, which is exactly what we're looking for, so that we can say our critical value of z, or as the cool kids say, z crit, is 1.96. Any number bigger than that, positive or negative, is unusual enough that we will call it statistically significant and say that our null hypothesis is unlikely and should be rejected. So a value of +2 or a value of -3.1 would be significant because they fall outside of that range. A value of 1.91 would not, because it is within that range. We only want things outside of that range. So where exactly did you pull that number from? Well, remember that the normal distribution has properties that say how much data falls within a given range, like when we calculated a z-scores. If you're ever in doubt and need a different spot on the graph, maybe you want to be right 99% of the time instead, you can use what's called a z-table, which is a table that has probability cutoffs for each value of z. Okay, so we have our hypotheses and our critical value of z, and now we can do some real calculating. First, let's write down our known population mean, because we're going to need that. Next, let's calculate the average for our sample. If we add these up, we get, let's see, 10 plus 4, 6, 10 is 20. And we have an n of 4, our sample size is 4, so we divide by 4, and that gives us our mean of 5. Now we're getting somewhere. My favorite part, time to calculate the standard deviation. If you recall from the standard deviation video, the formula for the standard deviation is as follows. Now, sometimes the top part of this equation is called the sum of squares. Calculating a sum of squares has two key elements that you have to master, the summing and the squaring. The order of operations is critically important to remember here. Always square first, sum later. Let's break it down into steps. First, we're going to subtract each one of these from the mean. And once we've subtracted them all from the mean, next we can square each one. This is easy because 0 squared is 0, and the other things are 1s. And finally, we can sum them, which is easy enough. Now that we have the sum of squares on top, we need degrees of freedom on the bottom. Yoplait puts fruit on the bottom. We put our degrees of freedom. We have one sample, so that's easy, n minus 1. 4 minus 1 is 3, so that's square root of 2 over 3, which equals 0.816. Now that we have the standard deviation, we can use that to calculate our standard error of the mean. So here's the formula. The standard error is equal to the standard deviation divided by the square root of the sample size. If we plug in our numbers here, we get 0.816 divided by the square root of 4. Square root of 4 is 2. So 0.816 divided by 2 is 0.408. And that's our standard error. We can plug it in down below. Now we can calculate our value of z that we observed. Z equals x bar minus mu divided by the standard error. If we plug in a few numbers here, we get 5 minus 2 divided by 0.408, which is 3 divided by 0.408, which is 7.35. So our z equals 7.35 for this sample. Now, the moment of truth. Was our z value unusual given the null hypothesis, or was our result just likely due to random chance? We don't know what the probability is exactly, but we do know that the probability gets smaller and smaller due to chance the farther away from the mean you go. As z gets bigger, the p-value associated with that z gets smaller and smaller. Our value of z was bigger than that, so even though we don't know what the probability is, we know that it's less than 0.5, and that means it's a statistically significant result. So we can say our observation is unlikely due to chance, meaning we should reject our null hypothesis, leaving only the alternative to take its place.
Hey, aren't you forgetting something, Daddy-O? I thought effect size was important to know.
Yes, it was a test and you passed. I haven't mentioned effect size. We know that statistical significance is not the same as practical significance. So we should look at how much we should care about this difference. To do that, we're going to calculate effect size, which for this test would be Cohen's d. Now the formula for Cohen's d is to take the difference between the means, just like the z-test formula, but this time we're going to divide by the standard deviation instead of the standard error. So if we plug in some numbers and do the calculations, we wind up with 3.68 as our effect size measure. Now what does that mean? Well, published guidelines suggest that 0.2 would be a small effect size, 0.5 would be considered medium, and 0.8 and higher would be considered large. So in this case, we have a large effect size. Okay, calculations completed.
Yo, this cat's assignment's for a t-test, not a z. So where is that t-test that you promised me?
Okay, here's the deal. If you can calculate a z-test, you can calculate a t-test. The difference lies in the sampling distribution you compare it to. Rather than the z distribution, you use something called the t distribution. Now, I'll give details on this in my upcoming video on how beer changed statistics. But in the meantime, the only thing you really have to know is that the critical value we compare against will be different. It's not going to be 1.96. T distributions will change as your sample size changes. In order to find your critical value, you will first determine your degrees of freedom based on your sample size and go to a t-table to find the value you need. So in our case, our degrees of freedom is 3. And then once we go down to our degrees of freedom, next we have to go across to our alpha, in this case 0.05. You will need to find your critical value of t. Now, if it asks between a one-tailed and a two-tailed test, we're going to do a two-tailed test. I'll have more on one and two-tailed tests again in a future video. So in our case, we need a calculated value of t greater than, it looks like 3.182 in order to get a significant result, according to this table. The formulas and everything else are the same. The only thing that changes is the number we're comparing against at the end. Now notice if I scroll down this t-table, if I get to a high enough degree of freedom, the t-test critical values get closer and closer and closer to 1.96. With a large enough sample size, a z-test and a t-test are exactly the same. Generally speaking, they say you should use a t-test if the sample size is less than 30. But really, why not just always use the t-test, since the results are going to be the same at higher sample sizes anyway? Safer bet, t-test. I once asked a friend of mine why he didn't say much, and he replied, "Why use lot word when few word do?" I think the same goes for statistical tests, so just use the t-test.
My number is negative. Explain this if you're able. I don't have negative numbers in my t-table.
That's fine. Because the sampling distribution you're testing is normally distributed, it's symmetrical, meaning you're going to get the same probability whether your t-test is positive or negative. In other words, you can more or less ignore the sign and treat it as a positive number.
Hey man, thanks a lot, but another question, you dig? My numbers were off slightly, so my p-value's too big.
Most likely this was due to rounding issues. You can be precise as you like, but at the end, make sure you round to 2 or 3 decimal places. But if you're off a little bit, one way or another, it's not a big deal.
Your formula looks different from one I found in a book. Maybe you should give it another look?
I promise this is the correct formula for the one-sample z-test or t-test. Sometimes the formulas are the same but mathematically rearranged in some way so that they look different. For example, I could represent the standard error the way we've been doing it, Or I could square the top and the bottom and then take the square root of the whole thing instead of taking just the square root of the bottom. This is mathematically the same, even though it looks different. Also, sometimes people represent the symbols differently. Instead of X bar, they might use an M for mean, or instead of, for the standard error of the mean, S sub X bar, which I like for the standard error, they might use the letters SEM. But you know what? It's all good, man.
Hey man, these tests are out of sight. Mine was not significant, which proves the null hypothesis, right?
No! Oh, sorry. I didn't mean to alarm you. But no. Remember, we aren't proving the null. We're only seeing if we have enough evidence to disprove it. Failure to reject the null simply means we didn't have enough evidence to detect a difference. We can't tell if there wasn't a difference or if we just weren't able to detect the difference that was there. Either way, the null is the default position and it should be retained. But it leaves us open to becoming convinced by better evidence in the future.
It's a hip test, but I'm nervous, you see. Why can't you just tell me my exact value of P?
Well, there are ways to figure that out that sort of go beyond this video. But one way is if you use statistical software, it doesn't give you the critical value. It actually gives you the p-value directly for your observation. Okay, I got to talk about assumptions. Now, there are a few assumptions made when you conduct a statistical test like this. First is that your data is on an interval or ratio scale, that the data are independent from one another, they aren't influencing each other, and that the dependent variable you're measuring is normally distributed and there are no outliers. There are ways to deal with situations that arise when some of these criteria are not met, but that'll have to wait for a future video. For now, knowing that we are assuming these things are true before the test is enough. And if these assumptions are not true, it makes our test's validity questionable. Okay, I think that about covers it for this one. It's exciting. We did our first inferential statistical test. Yay! I'm proud of you. To sum up, we first determined what the critical value of the statistic should be that would indicate a statistically significant result. We calculated our statistic from the data we observed. We compared these two numbers to determine whether our sample crossed that threshold. We also calculated effect size in order to put the result into a more practical context. The only difference between the Z and t-tests are in the critical values we compare them against. But when in doubt, use the t-test. We've got more videos coming up, including how beer changed statistics, 1- and 2-tailed tests, and how to calculate t-tests with multiple samples. Be sure to like, subscribe, and stick around for more videos on the basics of statistical inference, especially as it relates to psychological research. Until then, keep thinking.
Man, they let some real weirdos in these days.